Hi, my name is Robin Coxe, and I'm going to be talking about software-defined radio in neutral atom quantum computing, and hopefully the title of the talk will make sense by the end. So I have a lot to cover in the next half an hour. I'm going to try and provide some background for what we're doing so the use of software-defined radio makes sense. So I'll start out by talking about what is a quantum computer, why you might want to employ neutral atoms to make one, how we go about creating quantum computations using neutral atoms, and the answer is with lasers. And what, more specifically to software-defined radio, the classical control system electronics that are involved in controlling the lasers, and how specifically we're using SDR and GNU Radio in our control system. So starting out, what is a quantum computer? Quantum computers employ a computational model based on the principles of quantum mechanics. And they were first postulated in the 70s and 80s when people began to realize that processes dictated by classical physics, i.e. classical computers, cannot be cannot simulate quantum mechanical processes in tractable timeframes. So people ask themselves, can we make computers using quantum mechanics to solve these problems? So both classical and quantum computers can be expressed in terms of a uniform set of reversible circuits. So we're all familiar with the classical computing model where you have binary bits and a set of universal gates whereby you can implement any Boolean function using only the gates in the set. And for instance, NAND and fan-out are a set of universal gates for a classical computer. And the quantum analog is a qubit and some quantum circuits. So qubits, so let me just start out by introducing some terminology, like what's a qubit. So the qubit is a fundamental unit of quantum computation, and the physical realization of a qubit is a two-state quantum mechanical system. So we're taking advantage of, in quantum computing, of the somewhat mind-bending oddity of quantum mechanics, and that a qubit is actually a coherent superposition of both the 0 and the 1 state. And when I say superposition, what I mean specifically is a complex linear combination of those two states. Sometimes you'll see in popular science literature people say a qubit is in both states at the same time, and that's not strictly correct. So qubits, this kind of complex linear combination is very precisely expressed kind of mathematically in terms of this notation. Alpha associated with the 0 state and beta associated with the 1 state. These are called probability amplitudes, and they're complex numbers. And these probability amplitudes, because they're complex numbers, can both constructively and destructively interfere. And the relative interference, the degree of interference, I should say, is quantified by the relative phase of alpha and beta. And the qubit actually collapses to one of these two states, 0 or 1, only upon measurement. So this picture denotes something called the Bloch sphere, which is named after a Swiss physicist named Felix Bloch, and it's a very convenient geometrical representation of a qubit. So the operations on qubits, these logic gates that I was talking about before as being the fundamental units of a quantum computer, can be quite conveniently visualized as rotations by an angle theta about the 3 axes of this sphere. A phase shift, which would be tracing a horizontal circle around the sphere, and something called a C0 gate, which actually requires 2 qubits, and it performs the NOT operation on the second qubit, provided that the first one, or the control qubit, is in the 1 state. So keep this Bloch sphere in mind, because it will help explain what I'm about to go into when we get in terms of manipulating these qubits. So just the operations on the qubits can be represented by rotations on the sphere. So what fundamentally are we doing with a quantum computer? So the inputs to a quantum computer are registers of qubits in an initial state, and the circuits are effectively interfering the components of the input according to a predetermined quantum algorithm that's programmed into the computer. And the magic of quantum interference results in the cancellation of all these probabilities except for the correct solution. I say these words, and it's like the more you think about it, the more your mind is blown. But the quantum mechanics is actually makes much more sense mathematically than when you try and say it in words. But one of the fundamental, another kind of weird consequence of quantum mechanics is when you have multiple qubits, they can be, you can put them in so-called entangled states, whereby the combined state contains more information than each qubit individually. So you need at least 2 qubit gates to take advantage of this entanglement, hence a 2 qubit gate being one of the fundamental building blocks of the quantum computer. You might have heard of quantum teleportation, whereby you can impart information from one entangled qubit onto another, regardless of physical separation. So people have thought about using this phenomenon for key exchange, for instance, and encryption. And entangled qubits can also enable the generation of quite random numbers. So, there's been a lot of news about quantum computing lately. And the one thing we should make clear is that quantum computers are very well suited for the types of problems that take very intractable amounts of time on classical computers, but are not going to completely replace your laptop anytime soon. And if you're interested in some more examples, this IBM page has a good list. I have a lot to get through, so I won't talk about the examples specifically, but there are numerous applications for quantum computing that people are starting to look at. So why use neutral atoms for quantum computing? We haven't heard much about neutral atom quantum computers until quite recently, but they do have several distinct advantages. Notably, neutral atom qubits have very long coherence times compared to some of the alternative approaches, upwards of 10 seconds. So when I talk about coherence, I mean the ability to actually do useful computation with a qubit. So one of the things that you'll hear about when people talk about quantum computing is fault-tolerant quantum computers, because when you have things that are perturbing the quantum system, they can effectively collapse the qubit and decohere the measurement, which we don't want. So we have chosen to use arrays of identical atoms that we cool and trap with a laser in an array. And so we don't have to deal with like semiconductor process variations like people making superconducting qubits have to, because we don't have to fabricate anything. We have chosen strontium, which is an alkaline earth element. And strontium and some of the other alkaline earth elements have an atomic level structure that's quite conducive to quantum computation. We can actually operate our system at room temperature, so we don't need huge dilution refrigerators or liquid helium. We actually read the system out by taking images, so we don't need dedicated electronics for readout. And neutral atom qubits are actually smaller scale than semiconductor qubits, and in principle, we can the number of qubits we can attain in our machine is only limited by the amount of laser power that we have. So all of this is brought to life through the magic of lasers, magnets, and atomic physics. So there's a lot of information on this slide, so I'm just going to kind of summarize what we're doing with the lasers and the magnets. And basically, it all comes down to we need SDR to control this thing. So we're creating our array of strontium atoms by baking them off of it, boiling them off of a block of strontium in an oven. And then we use a laser beam that's propagating in the opposite direction from the atoms traveling down this path into the region of interest to slow down and cool the atoms. We're using magnetic fields to trap the atoms in an array, and then we use them to split the atomic energy levels into closely packed substates so that we can individually address the atoms with lasers and manipulate them into the states that we need for our qubits. And then we actually use lasers as well to do state-specific readout of the qubits by exciting the qubit that's in the 0 state, for instance, into an excited state, and then when it decays back into the ground state, it emits a photon, which we then detect with a camera. So we need very specific laser frequencies, and in order to get the atoms to behave the way we want to, we need to precisely control the duration, frequency, amplitude, and phase of a large suite of lasers in our control system at nanosecond timescales. And we need RF pulses to do that, and hence software-defined radios. So this just basically summarizes what I just said. So we're making a single qubit, we're cooling the atoms, we're isolating them in optical dipole traps focused by laser beams, then we're cooling them some more. And one point that should be made is when we fill the array, only on average about 50% of the sites are full, so we can fully fill the array, the computational region of interest, by moving atoms using the laser and RF pulses from outside the region of interest inside into the empty spaces in the array, so we have a fully filled array. And I'll show an example of that in a minute. And then once we have our array, we need to be able to address individual atoms and construct our gates and perform our quantum computations. So how exactly do we make a qubit with a strontium atom? Well, I will, essentially what we do is once the strontium atom is trapped in its trap, we are taking advantage of the fact that we are applying a fixed magnetic field. So there is a magnetic moment of the nucleus that's okay. Let me start again. So we have a strontium atom in the ground state. We apply a magnetic field. The magnetic field splits these ground state energy levels, and we take advantage of two of them to create our single qubit gate. And we actuate the gate through an off-resonant coupling to coherently rotate between the 0 and 1 states on the sphere. And so we use a laser to two laser beams, one to excite the 1 state into an off-resonant excited state, and then second one to de-excite it to the other state. So we can create an X gate, which is a pi rotation around the x-axis and flopping from 0 to 1 with these two laser beams. So that's our 1 qubit gate transition. And for 2 qubit gates, we take advantage of the fact that strontium atoms are so-called Rydberg atoms. So what a Rydberg atom is you can excite the strontium atom to a very large principal quantum number using a UV laser. And so in this case, the laser has a wavelength of about 317 nanometers. And the Rydberg atom has this very bloated electron cloud. So the electrons kind of expand out like this. And so the net effect of this bloated electron cloud is it has a dipole interaction with its neighbor, such that it shifts its neighbor's excited state to a point where this laser cannot actually, its neighbor's excited energy level is off-resonant, and it cannot reach this state. And this phenomenon is called a Rydberg blockade. And we can take advantage of the Rydberg blockade to create entangled 2 qubit gates. So it sounds crazy, but it does actually work. So now that we have our 1 and 2 qubit gates in our neutral atom quantum computer, how do we actually use it for computing? So here is a diagram of our stack, and the control systems group is down here. So we're kind of manipulating the atoms with our SDRs. Higher up the stack, that we're also at Atom Computing working on a language for specifying these quantum circuits called Klingon. So it allows people using the apparatus to string series of quantum logic gates together to form algorithms at a higher level. So the members of the control systems group are basically the non-quantum engineers. So essentially what we're doing is representing our quantum circuits as RF pulses. So the area under the pulse determines exactly how much of our population we transfer from one state to another. And the shape of the pulse has a huge effect on the performance of the gate. So the SDR needs to very precisely control the amplitude, phase, and frequency of this pulse. How do we use a software-defined radio to create a 1-qubit gate? So I talked about this process to go between 0 and 1 with our qubits. And so the way we actually actuate this is by running a laser beam through something called an electro-optic modulator, which essentially imprints the frequency that an RF frequency onto this laser beam, and in the frequency domain, kind of gives it this frequency kick that's necessary to bump these atoms to this virtual excited state and back down again. And so in practice, the SDR is using, because we're using the Xilinx RFSoC, so it has a maximum output frequency of 6 gigahertz. We need external mixers, so we have 2 laser beams, so that's 4 DAC channels. And the other thing we need to be able to do is selectively address the trapped atoms with RF tones. And so we use this, we do this through this device called an acousto-optic deflector, and essentially what it's doing is it's translating the frequency of tones applied to it into deflection angles. And you can, when you have 2 of these cross devices, you can individually address all the atoms in a 2D array by just applying multiple tones to this AOD device. So some of the enabling technologies for this SDR that we need are this programmable pulsar. It is effectively a wired SDR. And so we can also use software-defined radios to monitor laser frequency locks. I'll show you an example of that in a minute. So since at the time when we were designing the system, there was no cost-effective commercial available SDR that could transmit above 8 gigahertz, and we need closer to 10, we're making our own. And in addition, we need the control system to be scalable and replicable, because we do have plans to build additional computers in the next 2 years. So we took advantage of the fact that that in particle physics, the MicroTCA standard, which is a derivative of the telecom advanced TCA standard, has been widely used. So there are many commercially available FPGA cards that we can use, and there's many open source hardware designs that we can modify for our purposes. And we're also using electron multiplying CCD cameras that are commonly used in astronomy as well, and other scientific imaging to read out our system. So again, we're addressing 1-qubit gates, and we need 8 DAC channels. So very conveniently, there are 8 DAC channels in an RFSoC. So our system includes an RFSoC and some 2 marquee mixers for up conversion for the electro-optic modulator channels for the 2 legs of the 1-qubit gate. And we've implemented a custom waveform generator in the programmable logic and in the ARM core of the RFSoC. So the AWG is in CPU and FPGA and RF land, and these EOMs and AODs transition to the lasers to manipulate the atoms to create quantum computations. So the architecture of our Hapyxelor SDR, and it's called Hapyxelor because it's named after a mythical Canadian lake monster, because 2 of the guys who worked on it originally are Canadian, and that's what they named it, so it stuck. The architecture of our device is quite similar to most SDRs. We have the DAC, the RF chain out here. We have some of the the waveform player, which is capable of creating linear waveforms, single tones, ramped and chirped waveforms, ramps that are both linear and nonlinear, and arbitrary waveforms like those Gaussian pulses that we need to actuate the 1 qubit gate. Those are all FPGA blocks. And then in the ARM core, we have a gRPC server, which is running in C++, and it's implemented in C++ and Rust. And that is receiving commands from the host PC, from the higher level languages that specify the gates that are compiled down to the pulses and some digital triggers that we need. So this is an example of some of the types of commands that might be sent to the gRPC server, like setting the frequency, triggering, arming some digital triggers, and then playing out the waveforms. So we can have multiple waveform players because for in the case of the AODs, we need multiple tones per DAC channel associated with one DAC, and they're encapsulated by this module called a channel manager. And we also have a digital trigger manager that's responsible for triggering external devices like laser shutters and the imager when we want to take a picture, etc. So here's an example of what the instructions look like to program this thing, and we send trigger words periodically with durations, and then so you specify, for instance, say wait for trigger, and then specify the frequency, specify what you want the phase and amplitude profile to be, and then off you go, and out comes the pulse. So the RFSoC also has 8 ADCs, which are originally put on the chip for to act as like a receiver for a base station, for instance. But we're actually using them. We have DC coupled them, and we're using them to measure photodiode voltage outputs that scale with laser intensity. So it's like massive overkill for the RFSoC ADC, but they're there and it works, so we use it. And so we use the ADCs as an input to a digital PID controller to amplitude modulate the RF DAC outputs. And this capability has the bandwidth of the digital servo is limited by the latency of the ADC FPGA DAC path, but it's typically hundreds of kilohertz to a megahertz. And this functionality is being integrated into our system kind of basically right now. It's a new feature. So the reason why we're developing our own SDR is this picture on the left is what our system looked like before. It's a kind of collection of commercial boxes. Each of these boxes is two RF channels. So every time we want 2 more RF channels, we need to add another box. There's this kind of trigger patch panel, which is coming out of ribbon cables at the back of these boxes. We have these analog PID controllers that only handle 1 channel. So again, if you want another channel, you'll have to add another box. So this is not a very scalable model, but it was good it worked fine for our prototype. So what we've been doing is we're designing this SDR to be a MicroTCA card, but we're prototyping with a Xilinx CCU111 RFSoC eval board, and it's actually lurking down at the bottom here. So what we're doing is we're gradually adding functionality to Hapyxelor and decommissioning these commercial boxes one by one. And so the end goal is to replace that entire rack with a MicroTCA chassis. And every time we want 8 more channels, we just add one of these cards. So this is our SDR card. We actually are using our RFSoC system on module because it made the design a lot simpler. And then the way the MicroTCA chassis is constructed, we can have mezzanine cards coming out the back. So this is our digital trigger board coming out the back. I like penguins, so these are named after 2 of the penguins of Madagascar. And this board actually exists, and this board is getting assembled right now. So here is Hapyxelor in action. So I mentioned that we can actually pick up atoms from outside the region of interest and move them to fully populate the array. And it looks like the animation's not working, but what this bottom animation is showing is a single atom that's being dragged across the field of view of the camera by these ramped RF pulses coming out of Hapyxelor and spelling out the word atom. And this movie actually is showing a partially filled array becoming fully populated over time. So that is another kind of fun application and very useful application of our SDR. The other thing we're using software-defined radio for is we have this device called an optical frequency comb in our system, and it's an erbium-doped fiber-locked laser with a spectrum that's made of discrete equidistant frequency components. And essentially what that is the ultimate frequency reference. So when I say mode locked, what I mean is the laser outputs femtosecond scale optical pulses in the time domain that are separated by the round trip propagation time in the laser cavity. So in the frequency domain, you have, for some reason the picture didn't render, but you have very evenly spaced spikes in the frequency domain that are excellent frequency references. So the way we can use this thing to keep all of our lasers locked, and by essentially beating our lasers against this, mixing them with the optical frequency comb, and the beat frequencies are in the 28 to 100 megahertz range. So they're right in the sweet spot of a USRP. And I just should mention that this frequency comb won the Nobel Prize in physics in 2005, and one of the students of the Jan Hall, the Nobel Prize winner, is our scientific advisor at Atom Computing. So we're taking advantage of the fact that USRP N210 and a UBX-40 is right in the sweet spot for the beat frequencies to measure the beat notes of our lasers, take an FFT, and what we do is we measure the power spectral density in band and offset a few megahertz away, and we calculate the ratio of integrated powers, and we see if the power ratio is decreased, and we detect that with the USRP, and if the power ratio is decreased, we change the current set point, and this feedback loop keeps the lasers locked for a long time. So this apparatus is called LLAMA Long-term Laser Locking and Monitoring Apparatus. So no talk at GRCon would be complete without a flow graph, and this is a very underwhelming one, but it does have Mike's correct IQ block in it. We're not actually taking the FFT in this GRC block. When we were originally prototyping, we did, but the FFT is now actually being run on the host PC, and it's being fed into our real-time environmental monitoring display. So we actually have an Osmocom source in here instead of USRP source because we started out using a hack RF and then decided that a N210 would be better suited for this application. And so this somewhat underwhelming flow graph has increased the uptime of our lasers to order weeks when they came out of lock every few days before we installed this thing. So that is it. We are hiring software and FPGA engineers. And if you have any questions about the physics that I glossed over or any other questions about our system, I'll be around and I'm happy to answer them. Thank you.
Thank you very much, Robin. Are there any questions from the audience here? There is.
Hi, Robin. Thanks for the presentation. Hey, I was looking at the diagram for the RFSoC and I noted that some of the DACs you are using external mixing versus the internal mixing. Can you comment a little bit about the difference between those two use cases?
Yeah, so for the DACs without the external mixer, let me just find the slide. Those are driving the AODs, and one of the things I failed to mention is the AOD tones that we're outputting are in the range about 80 to about 400 megahertz, so you can directly generate them out of the RFSoC, whereas the EOMs in the modes that we are operating in to transition between the two states of the 1 qubit gate require 9 to 11 gigahertz tones. So we need to upconvert because the RFSoC's maximum output frequency is about 6 gigahertz.
Makes sense. Thanks.
Great. We have a few online questions, and then I'll jump over.
All right. From Arthur Lobo. What is the coherence time of neutral strontium atoms, or what is the coherence time of a neutral strontium atom quantum computer compared to superconducting and trapped ion quantum computers?
It's much longer, and what that effectively means is the qubit can be used for computation for for a much longer period, and so for neutral atoms, it's in the tens of seconds. The superconducting transmons, it's 10 to the minus 4 seconds, so the operations have to be executed much faster. And for trapped ions, it's in the hundreds of milliseconds.
All right. And next one, are the neutral atom qubits susceptible to cosmic radiation?
That's not something that we've thought about, but I suppose so. I mean, any perturbation could, in principle, decohere the system and would result in us having to use error correction. But I don't think it's our primary source of worry. Like things like temperature variations and electromagnetic interference and the lasers being unstable are far larger effects.
So question about the software architecture. I noticed that y'all use Rust. I was wondering if there was a particular reason you chose it and whether you had any regrets about that choice.
So the server was originally written in C++ and it was okay, but the Rust was actually more of an experiment than anything. It's the first piece of code that we've written in Rust, and so far the performance is great, where you have no complaints. It is, I can't tell you exactly how much faster it is, but it is faster. And it was kind of our first foray into using Rust in an embedded application. So stay tuned.
Any other questions? Yes. If you have questions, please raise your hand and I'll shuttle the mic during the answer.
This might not be the most intelligent question, but I'm just curious how you use lasers to cool something.
Oh, that is actually a very good question. So essentially what's happening is so the atoms are propagating down kind of a channel from the oven where they're boiled off from the block of strontium. And there's a laser that's propagating the opposite direction, which is at a frequency that is that excites the atom into an excited state. And so you've got the momentum factor slowing the atom down and cooling it. But also when the atom in the excited state decays back into the ground state, it emits the photon isotropically. So so you'd think you kicking it into an excited state, it would make it like actually not cool it, but the opposite happens. I'm not an atomic physicist, but that's my kind of understanding of how the cooling is working.
So this is a comment that I think basically attaches to this, but folks have seen most quantum computers having like room-sized coolers. This laser cooling is the alternative to that?
Yes, so we can use lasers to cool atoms, and you can also cool them through by trapping them in essentially a potential well. So if you put them in the right state with, magnetic fields that are trapping them in one place, they can't move, so they can't heat up either. But we don't need a cryosystem, but we can use one, and it can actually help us. But we don't need like the cryosystems to the scale of the superconducting devices.
Great. Seeing no other questions, thank you very, very much.